Good afternoon. My name is Michael Mattis from the Medgar Evers College CUNY, with my mentor and supervisor, Professor Andrew Aru, and today I will be presenting to you the electron drift states and LEAP lattices and the effects of circularly polarized light on these electrons. We will be examining the different types of materials to examine the band gap electrons on different types of models and materials, as well as looking at different type of formulas to gather data for such accounts. So here, one unique compound here that we could look at for these lattices is graphene. The unique property of graphene allows for linear dispersions due to its zero gap qualities on the z-axis. We'll be looking at it from a we were looking at the electrons on a two-dimensional scale. However, it isn't directly flat, so we also have to include the z-axis. But yeah, there's some displacement between the atoms perpendicular to the lattice, which creates energy dispersions. And the final electric field along the z-axis creates different electric differences between the two atoms, which again creates the energy gap. The zero band gap allows for valence electrons connected to the atom, as well as conductive electrons to move freely between the atoms, as shown in the image here. And this allows researchers to get conclusive results on the electric field and the conductivity of these electrons. This band gap is facilitated by another external electron field. A similar reaction can be seen in the compound silicene, germanium, and molybdenum disulfide, as they have similar symmetrical, band gaps. Now, a unique compound is a black phosphorus. Black phosphorus is the unique material for this research, as it is what we call anisotropic. This means that the values for the electron dispersion field will differ at different ends. So the conductivity of the current can prefer the x-axis more than the y-axis, which means that the results for the electron dispersion field can differ at different ends. This also means that the results derived from using this material depends on the angle examined for the black phosphorus. Now, the main objective is this research is to examine energy dispersions of the materials on flat bands, such as the alpha T3 lattice, as well as the dice lattice. On the right side, we have the dice lattice, and yeah, so this black area here is what we examine as the flat bands. Now, flat bands are very important as they represent no dispersion bands, which also means that the vector potential K will result in zero energy, and that all of the band experiences the same amount of energy evenly, as shown in the black square on between the cones, which in this case would be zero. The cones are direct cones, and each band represents a different type of electron. So here we have the on the top we have the conductive electrons from the atoms, and on the bottom we have the valence electrons from, again, the same atoms. This is unique to graphene, as this is the only material where a flat band is formed, thus making the research of this material extremely important. We can examine this by adding an atom to the center of the lattice, shown as the alpha T3 lattice, with the atom C being added towards the middle. By adding this electron to the middle, we could examine different types of interactions with other atoms, such as atoms A and B, as shown in the model. If these atoms are removed, the hexagon will consist of dispersions from the graphene atoms. However, a system will also be created for the C atoms. These C atoms are called hub atoms due to the location in the center of the hexagons, and while the A and B system from the graphene are called reed atoms because of the location at the ends of the hexagon. These interactions can create flat bands and add to the electron dispersions. Now, we anticipate to look at the result of the Hamiltonian by performing canonical substitution. Now, what this means is we look at the result of the sorry, we anticipate to look at the results of the Hamiltonian by forming a canonical substitution with the k vectors that we get from former um, experiments that we performed. But yeah, but we will substitute this k vector into the Hamiltonians to drive different results for the electron dispersions. This also takes into account the vector potential of the light introduced to the materials to gather different results. We also want to see the effect of different lattices on the energy dispersions as well as the effect of circularly polarized light. So we know that for graphene-like materials, the circularly polarized light creates these zero band gaps, and we wish to know why this happened and why so. We also wish to see how this light affects other band gaps, such as the existing one and the flat bands stated before seen in graphene. This is why we are comparing the dice lattice to the alpha T3 lattice, as the formula lattice has asymmetrical gaps, and we'll have different types of electron dispersion due to these different gaps. And yeah, we wish to continue this research. Um, and yeah, this is my presentation. Thank you. We hope to gather more results for June 24th, and yeah, we hope to see you there. Thank you.